Hello everyone, my name is Philipp. I'm a PhD student at University College London and will be presenting our work on generative modeling of BRDF textures from flash images. In this work, we present a novel approach towards high-quality material acquisition. For a given stationary flash image of a material, as seen here for marble, we seek to find its corresponding material properties. These properties are represented as diffuse, specular, roughness, and normal maps that, when re-rendered, resemble the input flash image. In order to capture materials from flash images, we collected a dataset of 356 photographs of various materials such as wood, leather, fabric, etc. All photographs were taken in a frontal-parallel manner with about a 20 cm distance from the surface. We also ensured the flashlight was the main light source during capture, and used 4 different smartphones for robustness. During training, we randomly sample flash images from our database and encode them using a resonant backbone into a compact latent space Z. For each training step, we also sample a random noise crop from an infinite noise field. We then reshape the noise conditioned on the latent space Z using a unit architecture. More specifically, after each convolutional layer, we reshape the statistics of the feature map using adaptive instance normalization. In order to do so, we feed the Z through a transformation layer T that maps it to mean and sigma values respectively. The unit then outputs SVBRDF maps. Next, we render the generated SVBRDF maps in a differentiable manner and compare the rendering with the input flash image. To this end, we feed both images through a VGG network and calculate the Gram matrix as well as the power spectrum in the Fourier domain on the resulting feature maps and compare these using AL1 loss. During test time, our architecture design allows us to fine-tune each test exemplar independently in order to improve quality. To do so, we keep the latent space Z fixed and further optimize the unit weights for each given example. This fine-tuning is only possible thanks to our self-supervised design. Next, let's have a look at the results of our method. Given an input image on the left, our algorithm produces diffuse, specular, roughness, and normal maps. Here, we can see a red plastic. As we can see, there are no repetitive patterns or any baked-in flash highlights visible. Having retrieved the BRDF maps allows us to relight the input. In this case, we show a red leather. Due to the design choice of making our method stationary and the fact that we reshape random noise crops to BRDF parameters, we can simply reseed the noise inputs, which outputs different variations of the same exemplar. Here, we show different realizations of tissue, metal, and leather. Our method also allows to generate infinite spatial fields of BRDF parameters without any border artifacts or repetitive patterns, and can even be upsampled infinitely as we can use any spatial resolution for the noise as input. Another property of our method is that we can interpolate different exemplars in latent space. On the left and right, you can see the exemplars to be interpolated. In the middle, we show a smooth transition from one to the other material. Here, we interpolate between a black leather and yellow zigzag fabric. In summary, we presented a novel approach that allows for self-supervised synthesis of BRDF textures from real flash images. Comparing this work with prior works, we introduced unique properties such as being able to generate infinite and diverse fields of BRDF parameters, and also our method does not suffer from flash highlights baked into BRDF channels. In the future, it would be interesting to increase the complexity of supported material, whether in terms of shading or non-stationarity. Also, not relying on fine-tuning to increase the network expressiveness would allow to create an even more cohesive space. The code and dataset is publicly available on our project page.